Hi everyone, welcome to Best Science Brain YouTube channel. Today we're looking at the mole concept. Introduction to stoichiometry, the mole concept. So before we go to stoichiometry of reactions, we have to understand what is meant by the mole. The mole is an idea developed by Avogadro. It seems like an abstract idea. It is a quantity that cannot be weighed using chemical balance, but can be calculated. So when we use mole in chemistry, the mole is more like a counting unit, just like the way we count our money in naira, or in pounds, or in dollars, or in whatever denomination you're using. The mole is the counting unit for chemists. Now, by definition, the mole, this is defined as the amount of substance which contains as many elementary particles as there are carbon atoms present in 12 grams of carbon-12 isotope. It's defined as the amount of a substance which contains as many elementary particles as there are carbon atoms present in 12 grams of carbon-12 isotope. So we're going to look at the mole definition once more. As we go ahead, we'll explain mole. Now, we look at the word molar mass. So these are concepts that will help us understand the mole. The molar mass is the mass of 1 mole of a substance. The mass of 1 mole of a substance. That is known as the molar mass. Look at the adjective qualifying mass, molar mass. That is mass of 1 mole of a substance. The molar mass of a compound is obtained by adding together the relative atomic masses of all the elements present in 1 mole of the compound. For instance, the relative atomic mass of calcium, that is Ca, carbon, and oxygen respectively are 40. That what means is that 1 mole of calcium weighs 40 grams, 1 mole of carbon weighs 12 grams, and 1 mole of oxygen weighs 16 grams. So the molar mass of calcium carbonate is calculated as, so we're looking at how do we calculate the molar mass of calcium carbonate. We add together the relative atomic mass of calcium, carbon, and oxygen, taking into consideration the number of atoms present. So calcium is 40 plus carbon 12, oxygen is 16, multiplied by 3. We now have 40 plus 12 plus 48, giving us 100 grams per mole. So the unit of molar mass is gram per mole, meaning that 1 mole of calcium carbonate weighs 100 grams. So that's why it's called molar mass. So we'll come here and say this means that 1 mole of the compound calcium carbonate weighs 100 grams. So the molar mass is the weight of 1 mole of a substance. So what if the substance is an element? What will 1 mole of the substance weigh? So we'll say similarly, the relative atomic mass of a metal such as zinc is 65. So zinc is an element. Since metals are monoatomic in nature, so metals occur as atoms, not molecules. It therefore means that 1 mole of zinc weighs 65 grams. So for a monoatomic element like a metal or noble gas, 1 mole of such element is equal to their atomic mass or masses. So zinc is 65. Helium, the atomic mass is 4. So 1 mole of helium, being a noble gas, is also 4 grams. Argon, the atomic mass is approximately 40. So 1 mole of argon, being a noble gas, is also 40 grams. So for compounds, 1 mole of a compound is equal to their molar masses as we saw in calcium carbonate. For elements that are monoatomic, 1 mole of an element is equal to the atomic mass. Then going to elements that exist as diatomic molecules. So taking diatomic molecules like oxygen, chlorine, hydrogen, nitrogen, bromine, iodine. So these elements are diatomic. You can see 2 on them: chlorine, oxygen, chlorine, hydrogen, nitrogen, fluorine, bromine, and so on, as instances. 1 mole of such molecules is equal to their respective relative molecular masses. So for such diatomic elements, we calculate their what's called the relative molecular masses. So taking oxygen for instance, the relative atoms of oxygen atom is 16. Hence, the relative molecular mass of oxygen will now be calculated as shown below, O2, which is 16 times to give us 32. Then it follows that 1 mole of oxygen molecule weighs 32 grams. So in this illustration we have taken so far, if the substance is a compound, 1 mole of the compound is equal to the molar mass. If the substance is a monoatomic element like metals, all metals, zinc, gold, sodium, calcium, magnesium, aluminium, the 1 mole of such metals is equal to the relative atomic masses. Then if this element exists as a diatomic molecule like these examples on the screen, 1 mole of such elements is equal to the relative molecular mass, that is the atomic mass multiplied by 2. So we'll move on. Now we'll move to the Avogadro's constant, or what we call the Avogadro's number. This is the number of elementary particles present in 1 mole of a substance. Remember, earlier on we defined a mole as the amount of substance that contains as many elementary particles as there are carbon atoms in 12 grams of carbon-12 isotope. Those elementary particles that are present in a mole, the number of elementary particles present in a mole is what we call the Avogadro's constant. And what are those particles that should make up 1 mole? Those particles are called atoms, molecules, ions, or electrons. So the elementary particles that make up 1 mole of a substance are atoms, molecules, ions, or electrons. So how many of these particles will make up 1 mole? That's the Avogadro's number, 6.02 times 10 to the power 23. For our previous example, we say that 1 mole of oxygen molecule weighs 32 grams. What it means is that in 32 grams of oxygen, we have 6.02 times 10 to the power 23 molecules of oxygen. Also, in the previous example, we say that 1 mole of zinc is equal to the atomic mass, which is 65 grams. It means that in 1 mole of zinc, I will have the Avogadro's number 6.02 times 10 to the power 23 atoms of zinc in 1 mole of zinc. We say that 1 mole of a calcium carbonate is 100 grams, that's the molar mass. It means that in 100 grams of calcium carbonate, I'm going to have 6.02 times 10 to the power 23 atoms of the elements present in calcium carbonate. So we understand the concept of the Avogadro's constant or number. This number represents the number of particles present in 1 mole of a substance, and these particles could be atoms, could be molecules, and could be ions, or could be electrons. So let's look at this illustration. Let this diagram, fig 1, represent a cup of rice. So if you take a cup of rice as a mole, and let rice represent a chemical substance, then the particles in this cup of rice are the grains of rice. So rice can be an element, for example, the zinc we use can be a gas like oxygen, can be a compound like calcium carbonate. So let rice illustrate any of the chemical substances we have just mentioned. The particles in rice are the grains of rice. So if this is 1 mole of rice, so how many grains of rice will make up 1 mole? And that is the Avogadro's constant. So I need 6.02 times 10 to the power 23 grains of rice to make up 1 mole of rice, should rice represent a chemical substance. So we say, assuming fig 1 above represents a cup of rice, that should be of rice. I made the correction. A cup of rice. If we should take rice as a chemical substance. Could be element, molecule, or compound. Then it implies that 1 cup or mole of rice should contain 6.02 times power 23 grains of rice, where these grains could be atoms if rice were to be an element, molecules if rice were to be a gas, or ions if rice were to be an aqueous solution of a compound. So we have explained that. We now go to another unique term using mole concept called concentration. Concentration can be measured in different terms in chemistry. So, but our concern here is that we're talking about concentration as the amount expressed in mole or in gram. Amount of substance either expressed in mole or in gram, dissolved in 1000 cm cube or 1 dn cube of water. So amount of substance dissolved in 1000 cm cube or 1 dn cube of water is what we call the concentration. Now, we'll look at some quantities used in stoichiometry or in mole concept, their symbols and their basic units. So we have number 1, mass. The symbol for mass is normally M. The basic unit is gram. We are not talking about the SI unit. In chemistry, the SI unit of mass is kilogram, but we prefer to use gram since we deal with smaller quantities in the chemistry laboratory. So for gravimetric analysis, we will normally take mass in grams. Molar mass, mm, symbol, then unit gram per mole. Amount, symbol is small letter n, unit is mole. Okay. Then concentration, which already defined these terms, can be expressed as symbol C or small p. That small p is called rho. So unit of concentration is mole per dn cube, sometimes written as capital N. So when we see capital M, it means mole per dn cube. So molar solution or gram per dn cube. So mole per dn cube, the unit of concentration C. Then the other type of concentration P, which is called mass concentration, unit is gram per dn cube. So having done that, let's see very clearly, gram per dn cube. So having done that, to continue, we are now going to look at number of moles or amount and formula for calculating number of moles present in any chemical substance. So see, the number of moles or amount present in a given chemical substance can be calculated with any of the following equations given below. So number of moles, small n, can be obtained using m over am, meaning mass over m is mass, and am is atomic mass or relative atomic mass of the element. So when do I apply equation 1? Equation 1 is applied when we want to find the number of moles of an element, a monoatomic element like metals and noble gases. So equation 1 is applied to calculate the number of moles present in monoatomic elements such as all metals, noble gases, and even certain non-metals like carbon, silicon, and the phosphorus. Although phosphorus could also be an exceptional case, because phosphorus can be tetratomic also. So now look at equation 2. Equation 2 says number of moles is mass over mm. So m is mass of compound or molecule, where mm is the molar mass or relative molecular mass or molar mass of molecule or compound. So equation 2 is used to calculate number of moles of a compound or molecule. So while equation 1, as we said before, you use to find number of moles of a monatomic element. So see the difference. So equation 2 used to calculate number of moles present in a molecule or compound. We look at equation 3. Equation 3 says number of moles is CV. That equation 3, where C, the concentration of the substance, dissolved solute, that dissolved substance in mole per dn cube, and V is volume of solution expressed in dn cube. So for that equation 4, volume must be in dn cube. We now go to equation number 5. Number 4. Okay, this is question 3 before this number 4, for equation 4. Equation 4 says number of moles N equal to CV over 1000. So you can see the relationship between equation 3, N equal to CV, and equation 4, CV over 1000 over CV all over 1000. What the difference? In equation 3, two of them are used to find the number of moles of a substance dissolved in a liquid that is a solution. So equation 3 is used when the volume of the solution is expressed in dN cube, while equation 4 is used when the volume is expressed in centimeter cube. So the 1000 under there is used to convert the volume to dN cube, because you know that concentration is in mole per dN cube, so volume should be in dN cube, so for it to be uniform. So 1000 cN cube make 1 decimeter cube. Okay. Equation 5. This one connects number of moles with number of particles. Small n is number of moles, while n subscript s is number of particles. The particles that make up a mole. What are those particles? We mentioned them before. Those particles will be atoms, electrons, molecules, or ions. So that's what NS stands for. While NA stands for Avogadro's constant. NA stands for Avogadro's constant. So you can see there, NA stands for number of particles, ions, molecules, and atoms, or even electrons. While N is Avogadro's constant, which is 6.02 times 10 to the power 23 particles. Then equation 6, number of moles of a gas. So this is gaseous mole, Ng, equal to volume of the gas at standard temperature and pressure all over 22.4 dN cube. That 22.4 there is a constant, while the volume of gas at the numerator should be expressed in dN cube for this to work. That's equation 6. So we say Vg at STP means volume of gas evolved or liberated at standard temperature and pressure, and Ng is the number of moles of gas liberated. As we go on, then volume, which is called the 22.4, which is called the molar volume of gas at STP, is 22.4 dN cube, is the constant formula. Then if the volume is in dN cube, the volume of gas Vg is in dN cube, then we have 22.4 the denominator. But the volume is in Cn cube, Vg is in Cn cube, then we'll convert 22.4 to Cn cube and multiply by 1000, so that the answer the volume should be uniform. Okay. Then let's say connecting the mole relations. We have different formula for number of moles. So each of them, the formula we describe from equation 1 to 7 represent number 1 to 6 represent number of moles. So we can connect any of them. If you connect equation 2 and 4, we have this. Equation 2 is mass over molar mass. You can go back and look at it. Equation 4 is CV over 1000. Each of them represents number of moles, so we can make the two of them equal to each other. So we connect equation 2 and 4, we get equation 7. So that is it. Then combining equation 2 and so when we use equation 7, of course, when we use equation 7, when all the items M, molar mass, CV are provided, maybe one of them is missing. Maybe you're looking for mass, other ones are given to you. You're looking for concentration, other ones are given to you, and so on. And that should be for a solution, because solution have to do with concentration and volume. Okay. Then equation 2 and 5. Combine equation 2 and 5. We have mass over molar mass equal to number of particles, S. S is number of particles. Particles could be atoms, molecules, ions, electrons, all over Avogadro's constant. So since both of them stand for number of moles, can equate them together and then look for an unknown value. Okay. Then connecting equation 2 and 7, we have equation 9. Equation that is for gas. Mass over molar mass equal to volume of gas all over the molar volume at STP. And that gives us equation 9. So let's take the first example. The first example says calculate the amount in mole present in 2.3 grams of sodium. So 2.3 represents mass. So the mass is 2.3 grams. And then sodium is a metal. And being a metal, we expect it to be monoatomic. So use the first equation, mass over atomic mass. That is 2.3 over 23. That gives us 0.10 mole. So as you can see underneath the explanation, sodium is a metal, hence is monoatomic. So that's why we use the atomic mass direct. So sodium cannot occur as Na2. It's not a molecule. Then we look at exercise 2. Determine the number of moles present in 5.30 grams of sodium triazocarbonate 4. They gave us mass. The mass, look at the solution, the mass is 5.30 grams. But this substance given to us in this element is a compound. So we have to get the right formula, Na2CO3. If you go back to the video we did on chemical equations and formula, you know how to get formula by valency exchange. So we calculate the molar mass, we get the formula right. Because if the formula is wrong, we're going to get the wrong molar mass and fail the calculation. So you have to make sure you have the right formula. So if you have not watched the first video on chemical equation and chemical formula, go back and then know how to derive formula of chemical formula of chemical compound directly. Do like a kind of a preview. In that compound, sodium maintains valency of +1, while the carbonic ion maintains valency of -2. So when they combine, carbonate will donate a valency 2 to sodium. That way you have Na2CO3. So find the molar mass of sodium carbon with the values in brackets. Sodium is 23 times 2 atoms, plus carbon, which is 12 in bracket, plus oxygen, which is 16 multiplied by 3, since there are 3 atoms in the formula. Adding everything together, the molar mass is 106 grams per mole. So we go back to the formula. Mole being a compound, equation 2 applies, mass over molar mass. So I divide 5.3 by 106. I'll get 0.05 mole at the number of moles. Go to equation 3. That says 0.250 mole of a substance weighs 10.0 grams. Determine the relative molecular mass of the substance. So look at the value given to us. 0.250 is the number of moles, while 10.0 is the mass. So from the solution, the number of moles small n is 0.250, mass is 10.0 grams. So what formula contains mole, mass, and molar mass? That is equation 1, which says mole is equal to mass over molar mass. So from here, we have already made the molar mass the subject, which is mass over mole. Substitute 10 all over 0.25 divide, have 40.0. So this is the molar mass, but we're not given a unit. Because we are asked to calculate the relative molecular mass. The relative molecular mass and molar mass are the same value, except that the relative molecular mass has no unit. Had it been that we are asked to find the molar mass, that would have been 40 grams per mole. But being relative, there is no unit on it. So, having done that, go to question number 4 that says, determine the number of moles present in 250 Cn cube of 0.1 mole per Dn cube HCl solution. Look at the difference. This is mole, 0.25 mole. This means number of moles. Unit is mole. But look at this one, 0.10 mole per Dn cube. That mole is current Dn cube. This one is concentration C mole per Dn cube. So you can see that the concentration is 0. This is not N. 0.10 mole per Dn cube. The volume of the solution is 250. We're looking for number of moles. One formula connects number of moles with concentration and volume. Number of moles is CV over the formula equation number 4. CV over 1000. So since we have concentration and volume, we substitute. Since the volume is in Cn cube, look at it, we have divided by 1000. Solving this, we have 0.0250 mole as the number of moles. Going to exercise 5 that says determine the number of moles of HNO3 acid present in 3 Dn cube of 0.05 mole per Dn cube solution. So this is volume. So volume of that C solution is 3.0 Dn cube. And this is concentration, which is 0.05 mole per Dn cube. So the number of moles is given by CV. Equation 5 applies here. Number of moles equal to CV. If you look at this exercise 4 and exercise 5 and exercise 4, they look alike. In exercise 4, we use N equal to CV over 1000. Why is there 1000 there? Because the volume is in Cn cube. So we have to convert the volume to Dn cube. That one will divide by 1000. So let's go back to where we are. Here the volume is in Dn cube. No conversion again. We now use N equal to CV. No 1000 is present there. So we now have 0.05 times 3, that gives us 0.150 mole at the number of moles. Now going to exercise 6, determine the mass of sodium triosocarbonate 4 required to prepare 250 cn cube of 0.01 mole per dn cube solution. Now going to the solution, the volume is given to us as 250 cn cube. The concentration is 0.01 mole per dn cube. Now since the substance is a compound, we'll find the molar mass using the accurate formula. Sodium is 23 times 2, carbon is plus 12, carbon is 12, all are given in bracket. Then oxygen is 16 multiplied by 3. So that gives us 106 grams per mole. So we have volume, we have concentration, we have molar mass, we're looking for mass. So equation 7 comes in, that combines the formula for different number of moles, CV 1000 and mass of molar. Everything given to us, their C is given to us, V is given to us, molar mass is no, we're looking for mass. So make mass the subject by cross multiplying, you can see it done, you make mass the subject, mass equal to molar mass times concentration times V over 1000. Remember that if the concentration is in dn cube, if the volume is in dn cube, 1000 will not be there, going to be CV over 1, and there will be no 1000 underneath. But because the volume is in cn cube, that's why you have 1000 there. Then solving and substituting the values obtained, 106 times concentration is 0.01, volume is 250 cn cube over 1000. When we solve, we have 0.265 grams as the mass of the substance required. Going to exercise 7, that says determine the number of moles present in 5.60 dn cube of hydrogen gas at STP. 1 mole of a gas occupies 22.4 dn cube at the molar volume. So stating our problem, volume of gas at STP is 5.6 dn cube. So how does volume connect to number of moles of gas? That is equation 6 or thereabout. So number of moles of gas given by volume of gas at STP all over the molar volume is 22.4 dn cube. The volume is already in dn cube, so no need to convert the 22.4 to any unit. So since the volume is in dn cube, everything is uniform. So divide 5.6 by 22.4, and that will give us 0.025 mole of the gas. Number exercise 8 says determine the number of moles of a gas present in 11,200 cn cube of chlorine gas at STP. Molar volume of the gas at STP is 20.4. So this question and the previous one look alike. Let's see the differences. So number of moles of a gas and volume are connected by the formula. Number of moles of gas equal to volume of gas at STP all over 22.4 dn cube. Okay, which is, since the volume now in this case, the volume now is given to you in cn cube. Look at the question, in cn cube. So we have to convert the molar volume to 2.4 to cn cube and multiply by 1000. So we now have 11,200 all over 22400 cn cube. Dividing, we have 0.05 mole of the gas. Exercise 9 says determine the number of moles of chlorine gas present in 17.7 grams of the gas. So they gave us the mass of the gas as 17.75 grams. And chlorine is a diatomic element, so it exists as a molecule. So find the molar mass. It's not a metal, so we should not use that 5.5 as the molar mass. So convert, we'll find the molecular mass, Cl2, that 5.5 times 2. At the beginning of this topic, I gave you examples of elements that exist as diatomic molecules. I gave you hydrogen, H2, oxygen, O2, chlorine, Cl2, nitrogen, I2, bromine, Br2, iodine, I2, nitrogen, N2, and so on. So this is the molecular mass of chlorine, 71 grams per mole. So now I use number of moles, mass over molecular mass, 17.75, the mass over 71, has 0.250 mole as the number of moles, because the gas is a diatomic substance. So go to exercise 10 that says determine the number of moles of argon gas present in 20 grams of the gas. Argon, the mass is 40. And I said initially that noble gases are monatomic. What are the noble gases? They include helium, neon, argon, xenon, krypton. So these noble gases are monoatomic. They are treated like metals in calculation. So to find the number of moles of the gas, we use mole equal to mass over atomic mass. So we multiply this by 2. We take the atomic mass here in the formula, 20 over 40, that gives us 0.50 mole. So the elements and noble gases, that I already mentioned them, they are all monoatomic. Now, exercise 11. Determine the mass of 11.2 Dn cube of chlorine gas at STP. Mass of 11.2 Dn cube of chlorine gas at STP. And we're given the atoms of chlorine at 5.5 and 1 mole of the gas at 22.4 Dn cube at STP. That's the molar volume of the gas. Then we go to the solution. The gas volume is 11.2 Dn cube. The molecular mass of the gas, remember that the gas is the atomic, Cl2. Multiplied by 5.5 by 2 to get the molecular mass or molar mass at 1 gram per mole. Then we have volume, we have molar mass. The connectivity is there. The number of moles of a gas given by volume of gas over 30.4, and also the number of moles of any substance is given by mass over molar mass or molecular mass. So that should be equation number 8 or 9. Equation 9. Connect them together, and then since we know everything here in this one except the mass, we make mass the subject. So mass becomes Vg times molecular mass over 20.4. Mind you that the volume must be in Dn cube for this to be 22.4. If the volume were to be in Cn cube, I'll multiply 22.4 by 1000 to come back to Cn cube. So substituting, mass becomes 11.2 times 21 all over 22.4. That gives us 35.5 grams. Exercise 12 says, determine the number of atoms present in 10.8 grams of silver bracelet. Atoms of silver is 108, and the Avogadro's constant is 6.02 times 6.23. In this question, we're not looking for number of moles, rather we're looking for the number of atoms. The atoms are the particles that make up a mole, as I said before. Those particles that make up the mole include atoms, molecules, or ions. The number of atoms present in 10.8 grams of silver bracelet. So, and you mind you that silver is a metal, so it's monatomic. Going to the solution, we apply the relationship mass over atomic mass, which presents number of moles of a metal, equal to number of particles over Avogadro's constant, which also represents number of moles. So the two of them are equal to each other. Since we know everything here except Ns, number of atoms, so make Na the subject of the formula by cross multiplying and making Na the subject. We bring in the values. The mass of the silver is 10.8. The Avogadro's number is 6.02 to the power 23, given to you in bracket. The atomic mass of silver is 10.08, being monatomic. We solve. We now have 6.02 times 10 to the power 22 atoms of silver in 10.8 grams of silver bracelet. Going to exercise 13 that says, calculate the number of molecules present in 22 grams of carbon 4 oxide. We are still looking for Ns because that Ns could be number of atoms, number of molecules, number of ions, or number of electrons. So the same formula or similar formula apply. But in this case, we no longer use mass over atomic mass as we we're going to use, as using this previous example. We're going to use mass over molar mass because the salt I'm giving to a carbon 4 that is a molecule or a compound. So instead of atomic mass under, we use molecular mass. So we make Na the subject as M times Na over molecular mass. The molecular mass of CO2 given to you as 44. So we'll go on to substitute. The mass of the CO2 is 22 grams, given to us in the equation. 22 grams of CO2 multiplied by the Avogadro's constant, which is in bracket all over the molecular mass. Solving, we arrive at 3.01 times 10^22 molecules of CO2. Exercise 14 says, calculate the number of molecules present in 11.2 Dn cube of nitrogen gas. So this is volume. They gave us the volume of the gas, 11.2 Dn cube. So then how does volume of gas connect to mole? That's the formula. Vg equal to 22.4 of Vg all over 22.4. That is the connection between number of moles of a gas and volume. And then we're looking for number of particles. The same, that is molecule, which is the particle now. Number of moles is also given as NS. This NS now stands for the number of molecules over the Avogadro's constant. So we'll go ahead and make NS the subject by cross multiplying. We'll have this. So we'll now go ahead and then substitute 11.2, which is the volume of the gas, times 6.02 power 23 all over 22.4. Mind the volume is in dn cube. 11.2 dn cube, then 22.4 shows the remaining dn cube. So solving this, we'll have 3.01 times 10 power 23 molecules of nitrogen gas. Exercise 15 says, calculate the number of hydrogen ions present in 250 Cn cube of 0.01 mole per dn cube. That 0.01 is concentration. That capital M, as I said initially, molar solution also means mole per dn cube of H2SO4 acid. So we're looking for a number of ions, the same NS. So S, as we say, stands for atoms, ions or molecules. But first of all, we're going to find the number of moles of the acid. The number of moles of acid in 250 Cn cube. Number of moles of acid given by CeV over 1000, which is the C is 0.1. There could be an error. The C is 0.01. Let's correct it. So go back. The C is 0.01 times 250, that's the volume, over 1000. So solving this, we have 0.0250 mole of the acid. So this is the number of moles of the acid, but it's not the answer. We're not looking for the number of moles, we're looking for the number of particles. Which particles? Hydrogen ions. So having obtained the number of moles of the acid, the next thing we're going to do is to ionize one molecule of the acid. We ionize one molecule of the acid. Ionizing one molecule of the acid. So we ionize H2SO4 to bring out hydrogen ion. So why should we ionize the acid so we can bring out hydrogen ion from the acid? Since our concern is on hydrogen ion, which is highlighted there. So we ionize the acid. Since the acid is basic, you have two replace hydrogen ion. You're going to produce 2 hydrogen ion and 1 mole of SO4 ion. We'll now start from the equation. In the equation, we have the number of moles of H2SO4 is the number in front, the coefficient. So the number of moles of H2SO4 is 1. When I say 1 mole of H2SO4 produce 2 moles of hydrogen ion. We don't have any business with SO4, so we do not eat. Our business is now the acid and what we're looking for, the hydrogen ion. So 1 mole of the acid produces 2 moles of hydrogen ion. Therefore, 0.025 mole of the acid will produce 0.025 times 2, which is going to be 0.050 mole of hydrogen ion. How did I get this 0.025? 0.005 was calculated before, which is the number of moles of the acid in the solution. So we'll continue. So by proportion, the number of moles of hydrogen ion is 0.05 mole. So this is the number of moles of hydrogen ion. But we're not looking for a number of moles of hydrogen ion, we're looking for a number of ions, number of particles. So from the formula that says, which formula? The formula that says, let's get it. This formula says mole equal to NS over NA. So we now make NS the subject. So formula says mole equal to NS over A. We now make NS now becomes mole times Avogadro's constant. And the mole of hydrogen ion is 0.05 times the Avogadro's constant. That will give us the final answer as 3.01 times 10^22 ions. So you want to find the number of ions is somehow a little bit tricky. You have to, first of all, you're not as straightforward as finding the number of atoms or number of molecules. You have to find the number of moles of the substance given to you, ionize the substance to bring out the ions, then work from the chemistry of the equation and then calculate the number of moles of the ions. And the example says, determine the number of moles of chloride ion present in 9.5 grams of aqueous solution of magnesium chloride. You are given Mg24, chlorine at 5.5, Avogadro's constant 6.02 per 23 ions. So this magnesium chloride will get the molar mass so that I can find the number of moles. So the molecular mass of magnesium chloride using the atomic mass in bracket, magnesium 24, chlorine is at 5.5 times 2, because of 2 atoms here. That gives us 95.0 gram per mole. This is the molar mass of magnesium chloride. Then you find the number of moles of the chemical substance being a compound using mass over molar mass. The mass of the substance given to us there is 9.5 in the equation. You can see that 9.5 in the equation. Divide by 95, you have 0.10 mole of the substance. The substance is not in solution. If it's in solution, we have gotten number of mole using CV over 1000 as in a former example before this. But the substance is not in solution. They gave us the mass to get the number of mole using mass over molar mass. So having done that, the same thing we did in the other one, you ionize one molecule of the substance, break it into ions. So when you ionize 1 mole of MgCl, you get 1 mole of magnesium ion and 2 moles of chloride ion. Then you now connect the magnesium chloride, which was given to you in the equation, to the chloride which you are looking for. You don't have the next magnesium ion. So now say 1 mole of magnesium chloride with the number in front of the magnesium chloride is 1 mole. The coefficient gave us 2 moles of chloride ion. Then therefore 0.10 mole of MgCl. So how did I get 0.10? You have been calculated before here. And the moles of the substance present in the solution calculated. So therefore 0.10 mole of MgCl give us 0.10 times 2, by proportion, times 2 of chloride. That gives us 0.20 mole of chloride ions. So the number of moles of chloride ion is 0.20 mole. The number of ions, which is obtained from the equation of mole equal to ns over Na, making Na the subject, which is the number of ions, again by mole times Avogadro's constant, which is going to be 0.20 times 6.02 times 423, and that will give us 1.20 times 423 ions. So that is the answer to the expression. At the beginner in chemistry, this will help you to understand further problems as you move into stoichiometry of reactions, how to solve problems that involve balanced equations. The mole concept is very important. So see the connectivity between mole, mass, concentration, and volume. Always stay connected to this channel. If you are not subscribed to the channel, move up to the channel's name, Best Science Brain, and tap on the subscription button only once and get subscribed. You only subscribe once and then you'll be seeing our videos. If you're a subscriber, you don't need to subscribe again. If you're a subscriber, you don't need to subscribe again. So remain focused, study with us online. Thank you for listening. Thank you very much. Thank you.